Imagine driving across the ocean. Then suddenly, the highway disappears beneath the water, not because it ends, but because engineers intentionally sent it under the sea, so the world's largest cargo ships could sail directly above your car. It sounds impossible, yet China turned it into one of the most ambitious transportation projects ever built.
Every civilization leaves a mark. These are the echoes of power.
Throughout history, bridges have solved one simple engineering problem. They help people cross water. But what happens when a bridge itself becomes the obstacle? Modern cargo ships are larger than ever before. Some stand taller than skyscrapers. Others carry more than 20,000 shipping containers across the world's busiest trade routes. Building a conventional bridge high enough for every ship would require enormous towers, longer approaches, steeper road gradients, and dramatically higher construction costs. Yet lowering the bridge wasn't an option either. International shipping had to continue without interruption. Chinese engineers faced a remarkable challenge. How do you build a highway across one of the busiest waterways on Earth without blocking the ships that keep global trade moving? Their answer wasn't to build higher. It was to disappear beneath the sea. The result became one of the world's most extraordinary bridge and tunnel megaprojects. A transportation system where drivers seamlessly transition from a bridge into an underwater tunnel before returning to another bridge on the opposite side. At first glance, crossing a wide stretch of water seems straightforward. Build a longer bridge, add taller towers, let ships pass underneath. Simple, but real-world engineering is rarely that easy. The route connecting Hong Kong, Zhuhai, and Macau crosses one of the busiest shipping corridors in southern China. Every day, countless cargo vessels, container ships, and commercial traffic move through these waters toward major ports that serve global trade. Closing that route, even temporarily, was never an option. Engineers first evaluated the possibility of constructing a conventional suspension bridge across the entire crossing. On paper, it looked possible. In reality, it introduced serious engineering problems. To provide enough clearance for the world's largest vessels, the bridge deck would need to sit extremely high above sea level. That meant building taller bridge towers, longer suspension cables, and approach roads stretching for many additional kilometers just to maintain safe driving gradients. The cost would rise dramatically. Strong coastal winds would create additional structural challenges. Aircraft operating near nearby airports would also impose height restrictions in certain areas. Then came another complication. Ships don't simply travel beneath bridges. They require wide navigation channels with carefully protected clearance zones. A single continuous bridge would place massive structural foundations directly inside one of the region's busiest marine corridors. The very structure designed to improve transportation risked interfering with another critical transportation network. Chinese engineers reached an unusual conclusion. The problem wasn't the water, it was the ships. Instead of forcing marine traffic to adapt to the highway, they decided the highway would adapt to marine traffic. That decision led to one of the boldest engineering ideas ever attempted. Sending a highway beneath the sea sounds simple. Dig a tunnel, pave the road, and let cars drive through it. But underwater engineering doesn't work that way. The seabed is made of soft marine sediments. Digging a conventional tunnel beneath such conditions would require tunneling deep below the ocean floor. That would make the route much longer, much steeper, and significantly more expensive. Chinese engineers searched for another solution. Instead of boring deep underground, they decided to build the tunnel first, then place it beneath the sea. This method is known as an immersed tube tunnel. Rather than excavating one continuous tunnel, engineers constructed enormous reinforced concrete tunnel sections inside dry docks. Each section measured well over 100 meters long and weighed tens of thousands of tons. Inside, every component was installed before entering the water. Roadways, ventilation systems, lighting, fire protection, emergency escape passages, even electrical equipment. Once completed, each giant tunnel segment was carefully sealed at both ends. Then something remarkable happened. The entire structure floated. Despite weighing tens of thousands of tons, the hollow concrete sections displaced enough water to remain buoyant. Powerful tugboats slowly guided each segment across the sea toward its final destination. But transporting the tunnel wasn't the difficult part. The real challenge was placing something that heavy onto the seabed with astonishing precision. Imagine trying to place a structure weighing more than a modern aircraft carrier onto the bottom of the sea with an error tolerance measured in centimeters. That's exactly what engineers faced. Before installation began, a carefully dredged trench was excavated along the tunnel route. The seabed had to be leveled with extraordinary accuracy. Even small irregularities could create uneven loads once the tunnel was in place. As each floating tunnel section reached the construction site, engineers connected massive hydraulic lowering systems. Ballast tanks inside the structure were gradually filled with water. Slowly, the floating tunnel began sinking. Not freely. Every movement was controlled. GPS positioning, laser alignment systems, marine survey vessels, and underwater monitoring equipment continuously tracked the segment's position. Powerful cables guided the tunnel downward at an extremely slow rate. Engineers compensated for waves, ocean currents, and changing tidal conditions throughout the operation. As the new section approached the previously installed tunnel, the final alignment became even more critical. Massive hydraulic systems gently pulled both sections together. Special waterproof seals compressed between them, creating a watertight connection capable of resisting enormous external water pressure. Only after extensive testing were the temporary seals removed. The underwater tunnel had grown by another section. Piece by piece, the highway slowly extended beneath the sea. But connecting tunnel sections created another engineering challenge. How do you transition from an elevated bridge into an underwater tunnel without drivers even noticing? A bridge cannot simply dive underwater. The change in elevation would be far too steep for vehicles traveling at highway speeds. Engineers needed a gradual transition. Their solution was to build two entirely new islands in the middle of the ocean. Not natural islands, artificial engineering platforms. Millions of cubic meters of rock and engineered fill were placed to create stable foundations above the tunnel entrances. These islands serve as the connection points between the bridge and the submerged highway. As drivers approach, the roadway slowly descends beneath the surface. The transition feels almost effortless. Yet beneath the pavement, complex retaining structures, waterproof barriers, drainage systems, and reinforced foundations work together to keep seawater outside while supporting the enormous weight of the roadway above. The islands also provide access for maintenance operations, emergency systems, ventilation infrastructure, and tunnel monitoring equipment. Without them, the bridge and tunnel could never function as one continuous transportation system. To most drivers, it's simply another stretch of highway, but hidden beneath the surface. These artificial islands quietly perform one of the most important engineering roles in the entire megaproject. And even after solving the bridge, the tunnel, and the islands, engineers still had to answer one final question. How do you keep an underwater highway safe every single day beneath one of the world's busiest shipping lanes? Building an underwater tunnel is an extraordinary engineering achievement. Keeping it safe every second is an even greater one. Unlike an ordinary highway, an underwater tunnel is a completely enclosed environment. There is no natural airflow, no escape onto the roadside, no room for error. Every vehicle entering the tunnel depends on hundreds of engineering systems working together simultaneously. Fresh air is continuously supplied through a powerful mechanical ventilation system. As traffic moves through the tunnel, sensors constantly monitor carbon dioxide, carbon monoxide, temperature, humidity, and visibility. If air quality begins to change, high-capacity ventilation fans automatically adjust their output. The goal is simple: maintain the same safe driving environment whether 10 vehicles or thousands are inside. Fire protection is equally critical. Heat detectors, smoke sensors, emergency telephones, fire hydrants, and surveillance cameras are installed throughout the tunnel. Operators inside a centralized control center monitor the entire system 24 hours a day. If an incident occurs, traffic can be stopped immediately. Electronic signs redirect approaching vehicles, while emergency teams receive precise location information within seconds. For most drivers, the tunnel feels ordinary, but hidden behind its concrete walls, thousands of sensors quietly ensure that ordinary journey remains possible. Yet protecting drivers wasn't enough. The tunnel also had to survive one of the harshest environments on Earth, the ocean itself. The sea is one of engineering's most unforgiving environments. Salt water accelerates corrosion. Ocean currents constantly reshape the seabed. Powerful typhoons generate enormous waves. And southern China lies within a region that can experience significant seismic activity. Every one of these forces had to be considered before construction even began. The tunnel sections were built using high-performance reinforced concrete specifically designed to withstand decades of exposure to a harsh marine environment. Special waterproof membranes and corrosion-resistant materials help protect both the concrete and the internal steel reinforcement. Around the tunnel, carefully placed layers of rock shield the structure from seabed erosion caused by tidal currents. This process, known as scour protection, prevents flowing water from washing away the supporting material beneath the tunnel. Engineers also incorporated flexible joints between tunnel sections. Although the entire structure appears rigid, these joints allow tiny controlled movements caused by temperature changes, foundation settlement, and seismic forces. Instead of resisting every movement, the tunnel safely absorbs it. Above the tunnel, massive cargo ships weighing hundreds of thousands of tons pass every day. Below, the highway continues operating almost unnoticed. It's a remarkable example of engineering adapting to nature, rather than attempting to overpower it. But none of these systems could function without continuous inspection, because underwater infrastructure never stops aging. When the bridge and tunnel system opened, construction ended, but the engineering never did. Every day, dedicated maintenance teams inspect one of the world's most complex transportation crossings. Inside the tunnel, cameras continuously monitor traffic conditions. Laser surveying equipment measures tiny structural movements. Drainage pumps are tested regularly. Emergency power systems remain on standby around the clock. Above the water, bridge inspectors examine expansion joints, support bearings, cable systems, and concrete surfaces exposed to the harsh marine environment. Below the surface, marine engineers monitor seabed conditions around the tunnel and artificial islands. Special survey vessels periodically inspect underwater protection layers to ensure currents haven't removed critical support material. Every inspection generates enormous amounts of data. Engineers compare new measurements with years of historical records. Artificial intelligence increasingly assists by identifying subtle trends that human observers might miss. This approach is known as predictive maintenance. Instead of waiting for something to fail, engineers identify potential problems while they're still almost invisible. To millions of drivers, the crossing feels effortless, a smooth journey across the sea. But behind that simplicity lies an engineering operation that continues every hour, every day, every year. And after solving construction, safety, marine engineering, and long-term maintenance, one final question remains. Did building a highway that disappears beneath the sea change the future of transportation, or was it simply one extraordinary engineering experiment? The bridge and tunnel crossing connecting Hong Kong, Zhuhai, and Macau is often described as one of the world's greatest transportation megaprojects. But could every country build something similar? Technically, yes. Practically, it's far more difficult. Projects of this scale require much more than engineering expertise. They demand decades of planning, extensive marine surveys, advanced construction equipment, and long-term investment. Before construction even begins, engineers must understand the seabed, soft clay, rock layers, ocean currents, shipping routes, wave conditions, and environmental impacts all influence the final design. Then comes another challenge: traffic demand. A crossing of this size only makes sense if enough people and freight use it every day. Otherwise, the enormous construction cost becomes difficult to justify. Countries like Denmark, South Korea, Norway, and Japan have successfully built impressive bridge and tunnel systems. But every project reflects its own geography. Some prioritize railways. Others focus on highways. Some rely almost entirely on tunnels. Others build record-breaking bridges. China's crossing demonstrated something different. Sometimes the best engineering solution isn't choosing between a bridge or a tunnel. It's combining both into one seamless transportation system. Because good engineering doesn't ask, "What structure should we build?" It asks, "What problem are we trying to solve?" And that philosophy is shaping the future of coastal infrastructure around the world. As global trade continues growing, transportation infrastructure faces new challenges. Cargo ships are becoming larger. Coastal cities are becoming more crowded. Environmental regulations are becoming stricter. And climate change is increasing the frequency of extreme weather events. Future bridge and tunnel systems will need to become smarter, not simply larger. Engineers are already developing digital twins that create real-time virtual models of entire transportation corridors. Thousands of embedded sensors continuously measure structural stress, bridge movement, wind loads, temperature, traffic volume, and vibration. Artificial intelligence analyzes this information every second. Instead of waiting for maintenance inspections, infrastructure will increasingly monitor itself. If unusual movement is detected, engineers can respond immediately. Some future crossings may even integrate autonomous traffic management systems capable of adjusting speed limits, lane usage, and emergency responses automatically. New construction materials are also changing what's possible. Higher performance concrete, corrosion-resistant reinforcement, and advanced composite materials promise longer service life with reduced maintenance requirements. The next generation of megaprojects won't simply cross oceans. They'll become intelligent infrastructure systems capable of adapting continuously throughout their operational life. And in many ways, this crossing became one of the first major examples of that future. For thousands of years, humans crossed water by going around it, or floating across it. Modern engineering changed that. First, we built bridges. Then, we built tunnels. But this project did something entirely different. It combined both into a single transportation system that appears almost impossible. Drivers cross the sea, disappear beneath the ocean, travel safely below some of the world's busiest shipping lanes, then emerge back into daylight without ever stopping. Most people experience it as just another highway. They never see the artificial islands hidden beneath the roadway. They never think about the giant tunnel sections resting quietly on the seabed, or the thousands of sensors constantly protecting every journey. That's the beauty of great engineering. When it works perfectly, it almost becomes invisible. The Hong Kong, Zhuhai, Macau crossing isn't remembered simply because it's long, or because it crosses the sea. It's remembered because it solved a problem that once forced engineers to choose between shipping and highways. Instead, they protected both. This is Echoes of Power. If you enjoyed exploring the engineering behind one of the world's most extraordinary bridge and tunnel megaprojects, subscribe for more documentaries uncovering the infrastructure, innovation, and engineering breakthroughs shaping the modern world. Because sometimes, the greatest roads aren't the ones that cross the sea. They're the ones bold enough to disappear beneath it.